All right. So I'm going to be recording part A for our final project. And that is to upload a video link for wing 2A, wing with AR10, a rectangular, core length 1, and then get these plots. Okay. Great. So first we'll open up XFLR5. And we'll do direct foil design. Make sure our spine foil is unmarked. And it wants a NACA 2415. 2415, 250. Okay. Awesome. We just did 250 points. And then just so we can see those points, it's kind of like our the resolution of our wing, or our airfoil rather. Great. And then from here, I'm going to be doing a direct analysis. Batch analysis, 415. Great. And from my previous run, we still have our 2 extra set points. This is just the Reynolds number based on our chord length and speed that we are traveling at, or our velocity. And then we have one more just so it's not the end point on our graph. T1, 1, 1. And then we have -6 to 16 increments of 1. That way we don't our outer bounds aren't our exact value. So we only need -5 to 15, but if we just do -5 to 15, we'll only get we'll end off on those values rather than encapsulate them like this. We'll do 3. Actually, we'll do 1 thread and make sure from 0 is unchecked. Great. Looks good. Now, we're going to be converting this into a wing. So we are going to define a new plane. Call it AR10, since that is the aspect ratio for 2A, which we are, yeah, 2A. AR10 chord length 1. So since we just want to simulate the wing, remove elevator, remove the fin. Chord length of 1, and it is rectangular, so both of those will be 1. No offset. No dihedral, no twist for this one. And then just do 5. That'll give us our span. We'll do 10 there. Ratio. Do we actually write? Yeah, aspect ratio 10. And then we need to set that to the 2415 foil. Looks good. Save that. I already named it, save that. And there is our wing. Why are we... Oh, we have to define analysis. Define the analysis, type 1, fixed speed. We're doing 50 for this. Where does it say? Yeah, 50 meters. Lifting line theory, -5 to 15, increment 1. 50 meters, and there's the RE that we defined earlier. This is LLT, lifting line theory. Save. Now we're going to do a sequence analysis, -5 to 15, delta 1, -5 to 15, delta 1. and analyze. Alright, our analysis is through. We can see our different drag, our lift. We can actually animate through the separate angles of attack. You can see the drag, lift, how they change. Side gives the best view. Yep. Now that we have that, we're going to go ahead and get our plots. Side. This is 2A. We want CL versus angle of attack, CL over CD versus angle of attack, CD versus angle of attack. So we have CLCD, CL angle of attack, CLCD angle of attack, and efficiency. Do we want efficiency? 1, 2. We only have 3. CL versus angle of attack, CL angle of attack, CD, CL, so CD angle of attack, CD versus angle of attack. So we'll convert this to CD angle of attack. So we have CD angle of attack, CL angle of attack, CLCD angle of attack, and we don't really need this. So those are our first 3 graphs. And off screen, I will just export these. Show you how to get the geometry. We've done that. We've plot these 3, and then at 5 degrees, plot the variation of local lift coefficient, induced angle of attack, and induced drag coefficient. Okay. So it wants lift coefficient. First we'll reset that. Lift coefficient. Look at that. And then induced angle of attack. Right, that's, yeah. And induced drag coefficient. Awesome. So we have gotten the geometry, converted it into a wing, and from that we've gotten the plots for CL versus angle of attack, CL over CD versus angle of attack, and CD versus angle of attack. And then, oh, it is at 11 degrees. Let's redo that really quick. Okay. So we have induced drag, local lift coefficient, I think. Yeah, lift coefficient. And induced angle of attack. Induced angle of attack. I think we did drag coefficient already, but we'll just do it again just in case. Yeah. And those are for 5 degrees. So we've gotten the geometry converted to wing. We've plotted these 3 graphs. And then for 5 degrees specifically, we have plotted the variation of local lift, induced AOA, and induced drag coefficient along the span of the wing. Awesome. Thank you for watching my video, and I enjoyed this class thoroughly.